All right. Now that we've defined all of our electrostatics quantities, we can come up with some cross relationships between electric field and electric potential. So, last time we discussed when we defined electric potential that there's this idea of something called an equipotential curve, also known as an isoline, where we have a curve that shows all values where the electric potential or height is the same value. And also, due to the fact that positive charges accelerate downhill, which we figured out using energy conservation, we know that the electric field must be directed towards low potential, or it slopes downhill. So this allows us to actually interpret the electric field as a physical slope of the potential of the terrain. So if we're thinking about a three-dimensional model of height, it is the steepness of the terrain, and we know it points downhill. So we can approximate the electric field by taking the change in potential and dividing that by the change in distance along a certain direction. So the electric field will always point in the direction of steepest decrease, and anyone with some calculus knowledge might connect this to the gradient. And that is true that this electric field is the gradient of the electric potential. And as a consequence of this, this means that your E field must point downhill towards low potentials, and it's perpendicular to all of these equipotential curves. Because if you're trying to get downhill as fast as possible, anything going along the curve would be a waste. So it must be directly perpendicular because that is your quickest route downhill. So here's an example. We can see that the field lines point from positive to negative, where the reds would be positive heights or hills, and the blues would be negative heights or valleys. And we see it's perpendicular to every one of those curves. So here's a familiar looking equipotential curve if we flip the page. So here's a set of lines. So we see that on the left, there's these negative heights, and on the right, there's these positive heights, and I have some points labeled. So what is a possible charge distribution that could create this set of equipotentials? Well, assuming we set V to be 0 at infinity, this means that any sort of positive heights have to be generated by positive charges. So there's likely a positive charge right here. And any negative heights are going to be generated by a negative charge. And we can see that this picture is perfectly symmetric about this midline. So we can assume the charges are also going to be the same magnitude. If not, you'd get some of these curves to be stretched out relative to the other. And you wouldn't get this 0 equipotential right in the middle. So this is a dipole electric field, which is two equal charges of opposite sign. So the magnitudes are the same, the signs are opposite. Let's say that there's an electric field line that connects A and C, and let's figure out the direction of the field and then draw its line. So there's two ways to approach this. The first way would be saying, well, the negative charge is on the left, and since negatives are sinks and positives are sources, it goes from C to A. Cool, that works. Using our new knowledge relating to potential, we said electric field points downhill to lower potential. So since C is at plus 10 and A is at minus 10, we know that A is at lower potential, so the field line points there. And now to actually draw it, we have to use our two rules of equipotential field relationships. So to relate the field to the equipotential, we say, well, first of all, we know it goes downhill. But it doesn't just go this way. It doesn't just go directly there. It has to somehow cross all of these equipotentials at right angles, because you have to get off at a steepest descent. So we just make any sort of curve that goes from C to A that looks roughly like a right angle at each of these points. So I did my best here. So this would be sort of how our field is oriented, where it goes from C to A. And we see that I tried to intersect both the 10 volt equipotential line and the negative 10 volt equipotential line at a right angle, as I did with this midline here. So it points from C to A, field lines point from high potential to low potential, or the negative charge on the left, so we could use source and sink rule. Now we're going to calculate a whole bunch of things. Change in potential energy in EVs of a proton moved from A to B. So here are some formulas we might find helpful. So we know that delta U is equal to Q delta V. We know that the work done by external forces is delta U, because that's the only way to add things to your bar chart. Right? Any changes to your total energy has to be caused by external forces. And then internally, the work done by the electric field has to be opposite that, or opposite the work done by external forces. So if we just want the change in potential energy, a lot of times a delta approach works really well for this. So delta U is just equal to Q delta V, and it goes from A to B. So I might actually write that down in my expression. It's not just any delta V. I'm going from A to B. So the reason we're using EVs is because we get a really nice unit, because the proton is just a plus E. And then for delta V, as I go from A to B, well, A is on this negative 10 volt line, and B is on the 0 volt line. So I have gained 10 volts doing that. So let's put a unit here. So this would be plus 10 EVs. Then we can look at the work done by an external force in units of EVs moving an electron from B to A. So the work done by external forces is the change in potential energy. So this would be, once again, Q times delta V, except we're going from B to A. So an electron is a negative elementary charge. And if we found that the potential from A to B is plus 10 volts, well, if I'm going from B to A, that's the opposite, so that's minus 10 volts. And notice we actually get the exact same answer. And that's due to this double negative involved. Because if a proton gains potential energy from going to A to B, then the work done by an external force in moving an electron from B to A, well, that means I'm just doing the opposite way, but also the opposite charge, so those two effects exactly balance out. All right, the work done by the electric field in moving a 2 microcoulomb charge along the path A, B, C, D. Okay, so you actually don't have to do this in 3 or 4 different steps, because we're just looking at delta V. And delta V doesn't care how you get from point A to point D, it just cares that you went from A to D. So first of all, the work done by the electric field, that's defined to be opposite the potential energy change. And I'm totally ignoring all these intermediate steps, because delta V only depends on the endpoints, because the electric force is what we call conservative. It's just like when climbing the stairs. You don't care if the stairs were spiral or not, the work done against gravity is the same regardless. So first of all, my charge is 2 microcoulombs, so that's 2 times 10 to the minus 6. And then from A to D, well, A is at negative 10 volts, and D is at positive 10 volts. So that would be plus 20 volts. So the work done by the electric field in this process would be negative 4 times 10 to the minus 5 joules. Or if you're a micro unit enjoyer, we could say this is negative 40 microjoules. And we can also reason that this should be a negative quantity, because if a positive charge moves from A to D, well, that's pushing a positive charge uphill, and the positive charge doesn't want to do that. Because again, the work done by a force is positive if the particle goes the way the force wants it to. And the electric force definitely doesn't want this particle to get pushed uphill towards the positive. So makes sense that it's a negative result here. All right, work done by the E field, moving a 10 nanocoulomb charge along the path CAD. Well, we'll actually do a quick simplification here, because if I'm going from C to D is actually on the same equipotential line. So delta V from point C to point D is actually 0. So this means that the work done is equal to 0 for all forces in this case. So you could work it out the same way. You'd just be multiplying the 10 nanocoulombs by some variation of 0. So that's another feature of equipotentials, because if you're on an equipotential, that means it is the same height. So it costs 0 energy to move freely along that equipotential, because everything there is at the same height. So there's no climbing or descending needed. Now we'll do an energy conservation problem. So suppose a point particle whose mass and charge are given are placed at C and then launched towards A, well, released from rest, and it flies towards A along the electric field. Calculate the speed of the particle. So anytime you're given voltages or potential values, you want to use the delta approach usually for energy conservation. So we use this fact that change in kinetic is always opposite the change in potential. And change in potential energy is Q delta V. So now we can go in and try to evaluate this if we'd want. Or I think we'll just do it symbolically and plug in at the end, because that's usually a good strategy here. So if we're going from C to A, well, let's just solve it out, because delta K would be 1/2 mvf squared minus 1/2 mv0 squared. So then we can just go ahead and solve this, because we're starting from rest, so that term is 0. So 1/2 mvf squared is equal to negative Q delta V. And then if we solve this for VF, it looks momentarily like we have a problem, because VF would be square root of negative 2Q delta V divided by M. So it looks like we'd be square rooting a negative, but it's actually not a big deal, because our change in potential can definitely be negative. So if we think about it, a positive charge will speed up if it goes downhill. So we are expecting this to be a negative answer. So we do know that this is negative 2 times our Q is 40 times 10 to the minus 6. Then our delta V, which better be negative, and then we'll divide by 0.04 kilograms. All right, so if we actually go up here, we see that C is at 10 volts, A is at negative 10 volts. So from 10 to minus 10, well, that's losing 20 volts. So I have decreased my height by 20, so the positive charge will definitely speed up because it accelerates downhill. And this nicely works out to exactly 0.2 meters per second. So that will be our final speed. So again, notice that the sign of delta V definitely mattered here. If you're working through it and you get some non-real answer, that usually means you just messed up a minus sign somewhere and you should just flip it. But of course, this does everything right. Now, you could have computed delta K first and you just get a positive number and it might be easier. So maybe instead you just calculated delta K and instead did something like VF equals the square root of 2 times K over M. Maybe you did that instead. That would have totally worked, because you could have calculated this delta K as 40 microcoulombs, as negative 40 microcoulombs times negative 20 volts, and you'd get something that works out. All right, here's another equipotential set. So we actually are interested in comparing the electric field at points A and B and justifying our answer. I am giving you a very small scale on the top that distance is 0.1 meters. So based on our thought that, well, electric field pushes downhill, and we can represent downhill as a slope, we know that the magnitude of the E field is approximately the slope of the terrain in any given direction. I just used R because it's not going to be directly horizontal or vertical. So the electric field magnitude is just roughly the slope of the terrain. So if I'm thinking about blowing this up in 3D, we see that near point A, the spacing is much, much smaller. We see that this very large positive spike near A is getting uphill much quicker than this negative spike near B. So using that fact, or just the fact sheet statement that says electric field is stronger when equipotentials are closer spaced, we can confidently say that the electric field is stronger at point A, because the spacing between adjacent equipotentials is less at A. So now we'll just create an estimate for the electric field strength at each point. So we'll see we actually get some new units for E field here that are equivalent to newtons per coulomb, which is one of the next problems. So if this is my scale up here, well, at point A, I'd say roughly this spacing looks like it could be one of those, but at point B, doesn't look like one of those, and it probably isn't two either. So I might say that A is one of those spacings, and B is 1.5. I definitely don't hate it if you pick something different. Like if you think B is exactly double the spacing, that's fine too. I could be wrong. But my magnitude of E at point A is going to be approximately equal to, well, let's see. I'm rising 50 volts because I go from 0 to 50. And I have 1 unit of spacing. So that's 0.1 meters. So I get approximately 500 volts per meter. And then similarly for the electric field at point B, we have to use the spacing we're given. I would like to have the E field or the equipotentials on both sides, but it's still the same 50 volt change, except this time it was spread over 1.5 ticks. So that's going to be roughly 333 volts per meter. So we can see that the E field strength is greater at point A, because just by the formula, if you're increasing the same number of volts over a lesser distance, that rate of increase, also known as the slope, is larger. And again, the key to making this work is that I made sure every adjacent equipotential was spaced by 50 volts. You can't do this analysis as easily if they're spaced by unequal amounts, but I can't imagine we would do that. So just like you can go from electric potential to electric field, we can also reverse it in the case of a uniform electric field, where we can say that the amount that your height has changed is equal to the slope of the terrain, E, times the distance you've walked parallel to E. Now, for people that use dot products, which is not me, if you're a dot product person, you'll see this formula written as delta V equals negative E dot D, where D is this displacement vector. I am not of that camp. I will show you how I do it. If you prefer to do this other ways, that's totally fine. I find that this works for most students. So, this equation applies for uniform electric fields, because obviously if your slope is changing, there's not just a single slope to multiply by. So this will transform into an integral if doing this with calculus. But for many cases, we're going to be using things like capacitors that generate uniform electric field. So we can just say the total height you've changed is equal to the slope of the terrain times the distance you walked along that. Now, the thing we have to do if we use this formula is this does not tell you sign. So you just have to use the fact that E points downhill and then decide if your height went up or down using that fact. And since E points downhill, if you're moving perpendicular to E, that's neither uphill nor downhill, so that's why there's a parallel in the formula. So if you are walking at an angle, use trigonometry to find the part that's either entirely with the field or entirely against it. So again, you do have to figure out the sign yourself of delta V. I just look at the E field. And if you're going downhill, that's going to be a negative potential, which is meaning the E field points that way, because E field points downhill. All right, let's verify that from this previous problem that newtons per coulomb and volts per meter are the same. I think it's probably easier to start with volts per meter. So let's say that the electric field could be defined as delta V over delta X, which is equal to volts per meter. Let's say we took that as our fact from the previous problem. Well, by definition, a volt is equal to a joule per coulomb. That is how we define volts all the way back in the circuit unit. And you can think about it as the energy per unit charge if we go back to the previous section. So this means that a volt per meter is equal to a joule per coulomb per meter, which is equal to a joule per coulomb times meter. But then also remember that from mechanics, or just the definition of a joule, is that a joule, which you can generate by doing work, is a newton times a meter, because work is force times distance. So this allows us to also go ahead and make that substitution, that a joule is a newton per meter, joule is a newton meter, so we get newtons times meters over coulomb times meters, and we see that the meters cancel. So we get a newton per coulomb. So, consistent. Sometimes we like to report the E field in volt per meter if it's a distance-related E field, but usually if we're doing forces, you'll see newtons per coulomb more commonly. They are totally equivalent, so just be mindful of that. A very common example of looking at E fields is lightning strikes. You might have seen like maybe a fact about this is how many volts a lightning strike is. This would be how they figure that out. So let's say that a lightning strike occurs from a negatively charged storm cloud 12 kilometers above the ground. So how this will work is we'll say that we have a nice big storm cloud up here, and we're going to say the negative charges are on the bottom of the storm cloud. This is our model for it. Again, it is just a model. And as a result, this can be modeled as a parallel plate capacitor, because if you have a bunch of negatives above something that is less negative, well, that is creating a capacitor, because relative to this cloud, the ground is positive. Even if it's not a net positive charge, it's still positive relative to the cloud. So now we can draw some E field lines using our source and sink rule and just properties of capacitors. So we said this is a very special E field that if you have two parallel plates, it's nice and uniform, which is why it's in this section right here. And what was also defined in the problem is that we are going to say that the bottom of the storm cloud is 12 kilometers in the air. So we're going to say this is 12,000 meters. So now what we can do is calculate the voltage difference between the bottom of the cloud and the ground. So our formula for potential difference in terms of E field is that the change in your height is the slope of your terrain times how far you walk along that terrain. And this is just the magnitude. So our E field strength, which was given to us in the problem, this is a fact that if your E field is very, very strong, it breaks down any material and turns it into a conductor. So it turns out for air, this is 3 million volts per meter. So that was given to us. So if there are 3 million volts of potential difference dropped every meter, and the storm cloud is 12,000 meters in the air, we can just multiply these two to get an absurd number of volts between the ground and the cloud, or potential difference. So it's the height difference between the two. And that's going to be, well, this is going to be 3.6. And then times 10 to the, well, I get 3 zeros and a fourth, so 10 to the 10th volts. And this is a huge potential difference. So this is what it would be in scientific notation. And let's see, billion is 10 to the 9th. So this is 36 billion volts. So much, much larger potential difference than our little 9-volt batteries in the lab. So you might see statistics like this. This is where it comes from. Of course, we approximated the E field as uniform, but we see we still get an absurd potential difference between the two. So now let's talk whether the ground or the cloud is at higher potential. So we also said that E field always points downhill. So if I look at my E field, because I said the ground was positive relative to the cloud, well, downhill to lower potential is the cloud. So the cloud is at lower potential, which means the ground is at higher potential. So since the electric field points from the ground to the cloud is at lower potential due to the downhill rule. So that must mean that the cloud is lower, so the ground is higher. Here's a common multiple choice setup where we want to calculate the potential difference going from A to B in each of these scenarios. And we do have to include the sign. So here's where we have to use the downhill rule along with the magnitude calculation. So the magnitude calculation, very straightforward, because we know that the magnitude of delta V is just ED parallel. And there's nothing weird happening angle-wise in this problem. So I have 1,000 volts per meter, or newtons per coulomb, doing that for 4 meters. So this is 4,000 volts. So I do know that the potential difference between A and B is 4,000 volts. But we're explicitly telling, given the info in this problem, that we're going from A to B. So there is going to be a sign. So in this case, we know that we are traveling downhill because we are traveling along the E field, which is downhill. So if I'm traveling with the E field, which is downhill, this means that delta V from A to B is negative 4,000 volts. So this means I'm going downhill. And again, here's like a quick way to think about it. If we use the source and sink rule, we know that negative charges are sinks. So wherever the field line is pointing to, it's going to be negative in comparison. So we know that the negatives are to the right. So this would mean that our potential gets lower as we go to B. So it is a decrease. All right, now this is the angled version. So we have an oddly specific angle here that we're traveling 5 meters, but all that 5 meters is not along the field anymore. So once again, we can use our source and sink rule that the negatives would be over here and the positives would be over here. So I'm actually traveling against the field. So this is actually going to be a positive potential difference between A and B as I travel to B, because I'm going uphill towards the positives. So once again, we can use the fact that the magnitude of delta V is just ED parallel. So we do have to figure out what that is, though, because it's not just 5, because the field is not at this angle. The field is horizontal. So we just want to find the horizontal components here. So we're just interested in this. So we see that we got a nice little right triangle here. So this is just going to be 5 cosine of 37 degrees, which is just equal to 4 meters. Because again, the 37 degrees is touching the side I want, and touching is adjacent, so I use cosine. You could definitely use SOHCAHTOA if you wanted to, but again, adjacent side, get it with cosine. So it is not 1,000 times 5. It's actually 1,000 times 4. So once again, the magnitude is 4,000 volts. But this time, I'm traveling against the E field, which is uphill. So this allows me to say that my delta V from A to B, in this case, is positive 4,000 volts. So we can actually check that it's actually given to us that this is the same potential difference magnitude in each of these parts, even though they look different. So we got 4,000 in A because we did just travel 4 meters along the field, but that's also what we did in B. It's just we traveled some extra distance that didn't contribute at all. All right, now for a ranking. So we have this plus Q charge, and it can be moved to a variety of places. So I might just automatically set up my sources and sinks so I can kind of figure out what's going on with the potential here. All the electric field lines are equally spaced, positive charge at the center, an external force moves it to each of these. Rank the work done by the electric field if I move from the starting point to A or B or C or D. So it is the work done by the electric field. So work done. We want the work done by the electric field, which is opposite the potential energy. So I'm taking the opposite of Q delta V. And Q is positive in this problem. So what I'm interested in doing is I'm really just looking at this change in potential. Now, we'll go through a forces approach, which many of you will find much easier. There's 2 unique methods of doing this. So first, we can see that, well, for B and C, the work is going to be equal to 0. Because B and C are neither against the field nor with the field. So that means the electric field does not care if you move from B to C, regardless of what charge you have. So B and C are 0 work done by the electric field. But if I go from A, if I go from the center to A, that's going to be uphill. And if you go uphill, delta V is positive, so this makes the work done positive by the electric field. Or sorry, this makes the work negative by the electric field. And conversely, this makes D positive work by the electric field. Because again, if we're looking at delta V, if I go to point A, I have increased my delta V, so I get negative, positive times positive, which is negative. And then if I go to D, this would be a negative quantity times negative, which is positive. Now, that is tricky, so the forces approach will work much better for many of us, but I'm just showing this general result here. So A was negative work, B and C were both 0 work, and D was positive work. So this was negative, this was 0, this was positive. So here's the first ranking. The work done by the electric field is just opposite the potential energy change. So this means the work done is positive if you move along the electric field, because that would make the potential change negative. But a lot of us might use this fact from mechanics that just says, well, work done is positive if you go the way the force wants you to. So in this case, the electric force wants the particle to move with the field. So anytime the particle moves with the field, it's positive work. Anytime it moves against the field, it's negative work. And perpendicular, well, work done is 0 if you're not displacing any direction along the force. So method 2 says exactly that. So the work done is positive if you move the same direction as the force / field, which agree for positive charges. So The work done is positive if you move with the field, and it's negative if you work against the field. All right. Now let's do some energy conservation with this fact. An electron is placed at the left end of a cathode ray tube. A uniform electric field is applied, and it exits the right end of the field after traveling a distance L. So first of all, let's draw the direction of the field within the tube. Well, we know that my electron is going to get shot out the right end of the tube with some final speed that I'm sure we're going to calculate. And if it's accelerating to the right, that means there's a force to the right. But we have to remember that electrons experience forces opposite the electric field because the electric field points the way positives will feel a force. So the electric field actually points left. And another way we could reason this is, well, if the electron is going to the right, that must mean this end is positive and this end is negative. So by the source and sink rule, the electric field points left. So this must mean that the electric field points left. So now let's find the speed of the charge upon exiting the tube. So again, anytime you're given field or potential difference, you want to use deltas for energy. So change in kinetic, because if you want speed, it's absolutely kinetic energy, some sort of problem relating to that, is opposite the change in potential energy, which is going to be negative Q delta V. So let's figure out what Q delta V is for this problem. So it is an electron. So an electron has charge -1 elementary unit. And then let's figure out what delta V is. So we do know that we weren't given delta V in this problem. We are instead just given the electric field. So we're going to use the fact that the magnitude of delta V is equal to ED. So in this case, it's going to be some variation of EL. And I see that my negative charge is climbing from the negative potential end to the positive potential end. Or I can see just by climbing the E field, it's going uphill. So this is a plus EL for my potential difference. And notice this works out because I get a positive kinetic energy change, which means our electron speeds up. So now we can go in and we can just set that equal to our change in kinetic energy. But U are 0 because we have no initial launch velocity. So we just set 1/2 mvf squared equal to E times big E times L, which gives us our final velocity of square root 2EEL divided by m. And this result should seem kind of familiar from what we did the other day with electric potential, and that's because compared to the result we got earlier, that we've been dealing with expressions that look like this before. So 2 times Q times delta V over M, it's just delta V is ED. So this quantity right here is just a potential difference, this EL. So that's why we get this square root relationship again. All right, last problem. No, not the last problem. Positive charge Q is traveling at an initial velocity V0 before entering a region of uniform electric field. The particle travels a distance d with the field and exits with non-zero speed. Find the final speed of the particle in each of the orientations. So first we're going to look at what happens if I travel at a velocity V0 this way, and my electric field is this way. So my positive charge travels with the field. Then we're going to do the same problem, except my particle travels opposite the electric field, a distance d along the field still. And then we're going to look at what happens if I travel a distance d with an electric field that's perpendicular. All right, so regardless, this problem is done the same way. It's just the effect of this electric field is going to be slightly different each time. So we know that the relationship we're interested in here is this delta K equals negative delta U equals negative Q delta V. And we know that delta V is ED. So we have some variation of ED that's going to go in here. So we're going to be interested in figuring out whether that's positive or negative in each of these cases. So in this case, same direction. Well, delta K is going to be negative Q delta V, which is negative Q times, well, I am traveling with the field. The field is pointing downhill. So this charge is moving downhill. So this is a negative potential difference. So I get a positive QED change in my kinetic energy here. So this allows me to set up this relationship, 1/2 mvf squared minus 1/2 mv0 squared is equal to QED. And then I could just solve this for VF. So just to spare us of that, well, let's do it once. So we can multiply by 2, divide everybody by m, take a square root, and in the first case, we'd get square root of VF squared plus 2QED divided by m. All right, so what we should notice about this is that this looks very kinematicsy. So you could have definitely done this using F equals QE and use the time-independent kinematics to do this. But also notice this. My final speed is equal to the square root of my initial speed squared plus something positive. So this means my particle will speed up, which is exactly what we expect, because a positive charge moving with an E field speeds up. Now, you can go through the steps and convince yourself of this, but I think it should be pretty self-explanatory that if the only thing I do is go against the field now, that's going to make my potential difference negative. Or sorry, that's going to make my potential difference positive, which is going to make me lose kinetic energy now. So this answer works out the same, except there is a negative splitting the two. And I did put in the problem that we can assume the particle does not stop, so we don't have any zero issues here. There is a point where the particle would end up stopping. And then perpendicular. So let's actually do this one again, or at least let's do the start of it. So we know that our delta K is going to be negative delta U, which is negative Q delta V, which is negative Q times, well, I'm traveling along the field again. It's just going to be traveling this perpendicular distance d, so it's going to be this angled velocity situation. So it is still just a downhill potential difference of ED, which is plus QED. And if we go through the math, that actually means our answer is going to be the exact same as the part A answer, because I gained the same amount of potential, or sorry, of kinetic energy in this case. But it should be noted that this answer is not totally identical to part A. Yes, the speed is the same in part A, but actually the velocity is different, because this time you're gaining perpendicular velocity. So this works this way because of the Pythagorean theorem. So instead, actually, your triangle, or your velocity, this VO doesn't get disturbed by the electric field at all, but you're actually gaining some velocity equal to this. 2qEd over m perpendicular to your initial velocity. So actually your Vf is this angled velocity. So it works out the same, but mathematically for slightly different reasons. So here, of course, your VO just gets slightly less long, and here your VO gets even longer, but in part C it also gets longer, but just in a different direction. All right, now time for our actual last problem. Group of students wish to calculate the uniform electric field magnitude E between the plates of a capacitor. So to do this, we're saying they are using ions of known mass to charge ratio. So there's that quantity again, that M over Q. We release it from rest at one plate and it slams into the other plate with some speed V that is magically measured somehow. We change the plate distance D and record the speed each time. We want to find the E field. So, of course, due to the fact that there's some sort of speed change happening, and just based on what we've been doing so far, we know this is going to be an energy conservation problem. So delta K is going to be negative delta U, which is negative Q delta V. So this means our delta K is just going to be equal to, well, our negative Q, what's our delta V? Well, we're given the electric field between the plates, and we are given that, well, we're not given it's a positive charge, but we can just assume that. So if this is a positive charge, my E field is going to point this way between the plates. So I know that I will be going downhill a distance D. So my delta K is once again positive QED. So now we can just set that equal to our kinetic energy. So our 1/2 mvf squared minus nothing is equal to positive QED. And we want to solve for E. So let's solve this. Let's get VF by itself, or VF squared by itself at least. So VF squared would be equal to 2QE over M times D. So this is what we have data on, is VF and D. So this means that we can graph VF squared on one axis and D on the other. And if we graph VF squared on the vertical, D on the horizontal, this means that our slope is going to be equal to 2 times Q times E divided by M. And notice we do know the fraction M over Q. So once getting our slope, we just have to do some rearranging to get our electric field. So one thing to be careful of in this, again, note that we have scaled up our velocities. So instead of writing all the scientific notation, each of these, there's a 10 to the 7th floating around. So I'm not actually going to do this, but you could fill in your squared velocities here if you wanted to. Of course, we don't need to watch me plot points. So here it is. And here's my rough best fit line. So notice I did actually square my 10 to the 7ths. So this scale factor becomes 10 to the 14th. So just be mindful of that. So then, just doing some linear regression in Desmos, this was the equation I got. And we used the best fit line because we said that the slope of our line was equal to, let's see, 2QE over M. So multiply by M over Q. So we'd get M over Q times slope would equal to E, because I got to send the M and the Q to the other side. So this means E is going to be 1/2 times M over Q, which was given in the problem, times the slope. Because again, this was given that this M divided by Q was 5.7 times 10 to the minus 12. And my slope that I calculated was 9.56 times 10 to the 14. So we're going to get an answer something in the 10 to the 3 range, and rounding mine, I got roughly 2,700 newtons per coulomb or volts per meter. Either of those are the same unit. There's a little best fit line action for us here. All right, there's our field and potential relationships.